What's up?
In your answer, there was no I in front of the omega cubed.
Oh, there's an I that comes out. So when you convert the exponential to sine, there's an I.
Oh, there is an I in front
and
there.
so that cancels out.
Cosine doesn't come.
Cosine does not. Yes.
What's up? 1, 2, D. Use the transform.
This one's on.
Sorry.
Let's see. I did. Yeah, I did 2 pages. Do one. You can do a baby and C. You can do 2. You just have to do 2. On the homework. Well, you're doing 2 right now, right? So yeah, we good. You only need 2 out of the 3. We did 1, we did 2. It's for practice.
It's like, yeah, he's so loud.
I wish I understood why a little bit more. Just the process. Because right now it's just do these things, kind of do these things. You know?
I just don't like how she's like, all right, this is what you do. Figure out the rest. I hate the drawings.
The
Kinematic ones. Yeah, the ones that you do. Doing last week. She chose like that. She transitioning to be the rotation.
Cross rotation or the.
Yeah.
Yeah, I'm sliding a little bit.
I mean, I can imagine. I really think this. Drawing it, and especially since you want all the drawings.
Cross the process, and that's it. Short bones.
We have like fucked up on that. So they kept me. Yeah, like straight back out.
On the final.
On the final?
I need to redeem that.
I'll think about it. I haven't even, the thought kind of has not even crossed my mind yet. All right, 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, good. Hanging in there. Okay, so today we are continuing our set of lecture notes on that we started on Tuesday. So today's gonna be all about random variables. So we kind of got to the, we're kind of a little bit ahead of schedule last time, so we started talking a little bit about random variables, but I did want to kind of review that a bit and then get more into kind of the meat and potatoes of what a random variable represents. Okay, so we talk about that today. After today, the next class session, of course, is going to be the midterm exam. So please make sure you are here for that next Tuesday, April 21st. Remember the midterm is in class. You have to be here for it. Same parameters as the first exam. So you can bring a 8.5 by 11 cheat sheet. You can have it both sides. You can write whatever you want on it. Except for the answer to the exam, but you would have to come from the future because I have not written the exam yet, so I don't even know what the solutions would be. Definitely use the homeworks to study, use the study guide. Homework 4 solutions I think are already up, but then now that I'm mentioning, I don't think I've posted a solution for homework 5 just yet. And of course, homework 6 solutions will come tomorrow after it's due. Okay. All right. I think that's about it. Any questions I can answer before we get started for today? Okay. All right. So let's go and get started. So remember the lecture for today and the lecture from Tuesday, not on the midterm exam, but you can expect it on the final. Okay. So where we're going to start today is we're going to start with the concept of random variables. Okay. So on Tuesday, we did kind of an introduction to this idea of probability and statistics, right? And kind of central to that whole discussion is the fact that, when you go, when you go when you go out into the real world and you're doing real life engineering measurements, engineering work, or even just, phenomenon on your daily life, right? There's a lot of uncertainty that affects how we kind of, there's a lot of uncertainty that affects, the things that happen out in the real world. Okay. And so for our purposes for this class, that means that, a lot of times when we kind of do the work and we do the analysis and we make a prediction, right? Oftentimes predictions are based on mathematical models. They're based on equations, differential equations. A lot of times, what happens in real world does not exactly match up to what we predict from our analysis. Right? Right. So we can spend, days, weeks, analyzing mass spring damper systems of kind of endless complexity, right? But there's always the caveat that, whatever we solve for, in on pencil and paper or in a computer, there's always going to be some degree of uncertainty where the real life is not going to match up with that exactly. Okay. So we started Tuesday talking about deterministic variables or deterministic events. And so a deterministic variable, the way that we often define it is we say that a certain variable has a singular value, right? Right. Right. So for instance, when we talk about our commute time, right? So we say that our time is equal to 45 minutes. So this is an example of a deterministic variable where our variable t has one singular value assigned to it, 45 minutes. Okay. Which, kind of seems like a strange way to describe it because, this is how variables are described for all of your other classes, right? So probably for every other math class that you've taken up until this point, right? All variables have had a single value. Just because, that's just how we kind of teach math. We teach math from a deterministic kind of point of view. Okay. Whereas, for a random event or random variable, our perspective kind of shifts a little bit, right? So for random variables or for variables that are affected by uncertainty, I think up until this point, the way that you've kind of dealt with uncertainty and kind of accuracy and probability, things like that, we kind of just say the shit happens, right? And then things don't really match up the way that we predict. But what I want to start now and kind of what I want to start over the next few weeks is to kind of really formalize the mathematical theory that can go around defining these random events. Okay. So the difference now with random variables, because they are affected by uncertainty and we don't necessarily know what their value is going to be beforehand, we have to kind of change how we define our random variable. Okay. And so by contrast, a random variable is not defined by a single value. It's instead defined by what we call a probability distribution. Right? So we can say that now our time t, right? So if little t here represents our commute time, right? That our commute time can take a range of possible values, right? And that range of values is represented by f, which we call the distribution function. So we'll define what that means in a second. So, that distribution function does have formal math theory. It does have a precise definition, and it's all about probability, right? Because for a random variable, the way that we kind of describe it in these informal theories, that every time a random variable is measured or every time a random variable is observed, it can take a different value. right? So kind of going back to our example of the commute time, right? Every time you actually go through your commute and actually measure your time, that is an observation or that is a measurement of that random variable. And every day you commute to school, it's slightly different because of the uncertainty that's involved. Okay. Okay. All right, and so next we'll define what that distribution function is and what it represents. And you know, I will say that, you know, I think when you're first getting into probability and stats, it is very intimidating because it's you know, it kind of takes a lot of what you've already learned for math and kind of, you know, views it from a very different perspective. So it's very disorienting. There's a lot of variables, there's a lot of terminology that gets thrown around. And so, you know, with the amount of time that we have left in this semester, you know, we obviously can't give it a really proper, thorough treatment. But at the very least, I hope to at least kind of lower the barrier of intimidation associated with probability and stats. So you kind of start to get used to the terminology, you start to get used to the concepts, so that, you know, when you go to apply this in your lab courses or other courses, then, you know, it doesn't feel as intimidating or scary. Okay. All right. Any questions on this? Okay. All right. So let's talk about the probability distribution function. Okay. Okay. All right. So the distribution function, it's defined like the following. Okay. Okay. So what we say is that big F here represents the distribution function. The notation that we use is we use a subscript here. Okay. Right. So this subscript, this T here, this represents the name of our random variable. So in this case, T is our random variable. So in other words, this is saying that this distribution function F is the distribution function for the random variable T. Okay. We're going to say this is going to be a function of X. Okay. And what this equals to, right? It's going to equal the probability. So this big P here, this big P represents a probability. The probability that our random variable T, right, when we observe it, right? So this T here, this is the value of T when we observe it. Okay. Is less than or equal to our function parameter X. Okay. Okay. So let me just write this because you know that's a bit confusing there. So let's write this as kind of a single simple statement. So the distribution function represents for various values of X. Okay. Right. And oftentimes we plot the distribution function. So this is going to be something we plot for various values of X. The distribution function tells you the probability that when we sample T or when we observe T, it's going to have a value that's less than that value of X. By the way, I hope my notes are a little bit clearer today. So I finally bit the bullet and bought a new stylus because the stylus I was using before was kind of dying. So, you know, my writing was getting more and more messy. So so hopefully this is nicer with this one. I kept putting it off because, you know, Apple pencils are not cheap. So I did the next best thing. I went to Best Buy, got the Best Buy brand Apple pencil. So take myself like 20 bucks. Okay. All right. So let's kind of debrief this a bit more. Let's see what that is. Okay, so I think the easiest way to kind of show this in action is to do an example. Okay. Okay. So once again, we're going to use our example of the commute time. I think that's the easiest one to do. I apologize. That's a lot of the examples you're going to see are going to be based on that. Okay. Okay. So the way the probability or the way the distribution function works is that, you know, you're gonna compare different thresholds, right? And then for each threshold, you're going to say, you know, what percent chance that your random variable is going to be less than that threshold. Okay. So for instance, you know, what if someone asks you, you know, what is the probability that, you know, your commute time is going to be less than 10 minutes? Okay. So based on where you start your commute from and how far school is, you know, what is the probability that your commute is less than 10 minutes? And you say that, you know, even on a great day, you know, even if, you know, every other human being on Earth just evaporated and there's no traffic, there's no way for me to get to campus in 10 minutes. And so you can say that the probability your commute time's less than 10 minutes is 0%. Right? Okay, and you say, okay, how about the probability that your commute time is less than 20 minutes? Okay. Right. Still, that would be 0%, right? Because maybe you live, 25 miles away from campus. And so, you know, trying to cover 25 miles in that period of time, not possible, right? 0%. Okay. So then we asked, how about 30 minutes, right? So what's the probability that you get here within 30 minutes? Well, you know, maybe you say on a really good day with no traffic, you know, maybe I can get here in less than 30 minutes, but it's pretty unlikely just because there's almost always traffic when you go. But, you know, we can give this a small percent chance. So we can say this is, you know, maybe 5 minutes or 5%. So 5% chance that you leave in the morning that you can get to campus within 30 minutes. And then we just kind of look at different thresholds here. And so, you know, we look at 40 minutes. And so what's the probability you get within 40 minutes? You say it's pretty good, right? And so maybe this is you know, maybe you make it within 40 minutes about a third of the time. So we say maybe this is like 35%. Okay. Okay. And then we can go one more up. So 50 minutes. And so, you know, you say most of the time you get to campus within 50 minutes. And so we can say this is maybe 80%, right? And then by 60 minutes, right? You never want to rule things out because you never know what can happen on the freeway. But usually 99 times out of 100 you'll make it to campus within an hour. So say this is 99%. Okay. So these values here, you can see that these values basically form the points of our distribution function. Okay, so traditionally the distribution function is not displayed like this, right? So I only displayed it like this just to kind of illustrate the point. Usually when you see distribution functions, it is displayed graphically. And so what you see here is usually a graph. Okay. So on the graph is the different threshold x. Okay. And then for the vertical axis, we have the distribution function of t as a function of x. Okay. Okay, so let's draw kind of the different thresholds here. So let's say we have 10 minutes, 20, 30, 40, 50, and 60. Okay. Okay, and so let's plot these values here. So at 10 minutes, 20 minutes, we have 0%, right? 30 minutes, we have maybe 5%. It comes up a little bit. 40 minutes, we come up here. 50 minutes, we're almost at 1. And by 60, we kind of maxed out here, okay? So the distribution function, if you connect the dots, would look maybe something like that. And of course, the maximum value for the distribution function is, well, I use percentages here. So, if you go in terms of percentages, it's 100. But usually we express percentages as a decimal. And so 100% would be the same thing as 1 point. Okay. So probability of 1.0 means 100%. Okay. So that's the idea with the distribution function, is that we know that we have a random event. It is subject to uncertainty, so its value is going to change every time that we observe it or measure it, right? But we can at least express, or we can at least quantify the probability that the value that we observe falls within certain thresholds. Okay. And so that's the idea. And so the distribution function just aims to quantify, the probability of our random variable taking certain values. Okay. All right. Any questions on the distribution function? Good. All right. So some properties of a distribution function, which are always true, right? One thing to know is that distribution functions are always going to be increasing up until it reaches the 1.0 threshold, right? And so the way that we say that mathematically is that distribution functions are monotonically increasing. So it doesn't make sense for our distribution function to decrease at any given point, right? Right? Because if you think about how it's defined, right? So if we say that our probability that our commute time is less than 30 minutes or 40 minutes, right? If we say that this is 35%, it doesn't make sense that if we were to go up, right? Just because we are using the less than or equal to or less than operator, it doesn't make sense for this probability to go down, right? And so, we can't say that, if the probability of t less than 40 is 35%, the probability that t is less than 45% can't be less than that, right? Right? So that makes absolutely no sense, because if t is less than 45, it's less than 40, right? Or excuse me, if it's less than 40, it's also less than 45. So it doesn't make sense for our distribution function to ever decrease. Okay. Okay. So keep an eye out for that. And so, always make sure that your distribution functions are monotonically increasing. Okay. All right. It has a max value of 1. Just because 1 represents maximum probability. Okay. And another name that you'll see for the distribution function is that these are often called the cumulative distribution function. Okay. Or sometimes it's shortened to CDF, right? But cumulative distribution function is a little bit of a mouthful, and CDF by itself is a little bit vague. And so, oftentimes you'll see me call it the distribution function. But just so that you know. Okay. Okay. And so another piece of trivia is that you can also use the distribution function to represent the probability that your random variable falls within a certain range. Okay. Because right now, all the distribution function tells us is the probability that our random variable is less than an upper threshold. But sometimes we want to have a lower threshold as well, right? And so if we say the probability that our random variable is between x1 and x2, okay? So in other words, maybe we want to find out, maybe the probability that t is greater than or equal to a, but less than or equal to b, okay? So this a here is our lower bound, and b here is our upper bound. Okay. And so the way we can do this is we can take our distribution function, so ft, we're going to evaluate at the upper bound b, okay? And then we're going to subtract the distribution function evaluated at the lower bound a. Right, so you can do that mathematical operation there just to do that. Okay. And oftentimes this is useful, right? Because oftentimes, if you have a random event, you want to find out if it's going to be within a certain threshold or within a certain range. So you can use the distribution function to do that. Okay. All right. Any questions? Any final questions on the distribution function before we move on? Okay. All right. So that's the distribution function, and so that's kind of the first representation of a random variable. Okay. So I kind of scroll back up here. Right? And kind of going back up to this definition here. Now that we kind of understand what a distribution function is, right? We can start to see, how we actually define a random variable, right? So we no longer have a single value. Now we represent it essentially with the function, or I think more realistically, we represent it graphically. Okay. Now the distribution function is a good start. I think that's kind of the easiest way to interpret it, or easiest kind of starting point for interpreting a random variable. But it's actually not the most common way for us to describe random variables. Right? So there's another type of function that we can use to describe a random variable called the probability density function. This also has a funny acronym, which is PDF. But of course, I think when people think of PDF, I think 99% of the time they think of the portable document format that's used on your computer, not the probability density function. Okay. So we like this idea. We like this idea that, since we know that random variables cannot, they can't be defined by single value, we like this idea of defining a random variable according to some kind of graphical representation. But oftentimes, when we look at a random variable, usually the first question that you ask is, what is the most likely value for this random variable? So if I were to measure this random variable right now, if I were to drive from campus back to my home, I want to find out what's the most likely time. And this is used a lot too. I mean, so if you ever use, a GPS, program on your phone, Google Maps, right? That's what Google Maps is essentially trying to do. They know that your commute from here, point A to point B, there's going to be a lot of uncertainty, but they still provide you with an estimate in terms of what your estimated arrival time is going to be. And right now, we can't exactly do that. Well, we can, but it's not as clear to pick that information out from a distribution function. Okay. So the CDF, I think, is a great way to show kind of overall probabilities for the random variable, just kind of where it kind of stands. But, if you were to look at a CDF and say that, I want to find out what's the most likely value that this random variable will take, it's not the easiest thing to do. Okay. In reality, it would be, the real answer to that is just wherever the slope of the CDF is the highest. But that's not always easy to kind of pick out at a glance. Okay? And so we can use probability density functions instead. Okay. And the whole idea with probability density functions is that they're meant to emulate the use of a histogram. So remember, we went over the concept of a histogram last time, right? We went over in a different context. So on Tuesday, when we presented histograms, we presented histograms as a way to visualize, a collection of data, right? So for random variable, we don't necessarily have a collection of data. We just know that we have a variable that is subject to uncertainty and randomness. But we like the idea of a histogram because the histogram tells you, a histogram very easily tells you that if you were to pick out a random sample from your data, right, it tells you, where you're most likely going to find that data. Okay. So just to kind of refresh your memory, right? A histogram looks like the following. Okay. So remember, to make a histogram, you would take each of the entries in your data table or each of the entries from your list of measurements and put them into particular bins. Okay. Where if there are more entries, in a particular bin, then they'll have higher values of in the histogram. Okay. So wherever the peaks are, right? Those values are most represented in your list of data. And so you're most likely, so if you just, you kind of close your eyes, you pick a random data entry out of your hat, you're most likely to find one in that bit because that one has the highest screen value. Okay. So probability density functions were kind of built off this idea, right? Where we can kind of visually look at a function and we can very easily pick out where the peaks and valleys are. And that'll tell you kind of most and least likely values that a function could take. Okay. Okay. And so a probability density function looks like a histogram, except it looks like a smooth function instead of a collection of kind of disjointed bars. Okay. And so if I were to draw a probability density function for this set of data right here, it would probably look kind of something like this. All right, and so if you view that red curve by itself, you can see that there are various peaks. In this case, we have a bimodal distribution. So there are two peaks, and so those are going to be the most likely values of that random variable. Okay. And so the probability density function is probably the most standard way to define a random variable. Okay. And so this is kind of where the probability statistics gets really interesting because there are certain types of density functions that are often kind of described in the literature, right? So one type of random variable that we talked about last time was a Gaussian random variable. So a Gaussian random variable has a very characteristic density function, which I think we kind of talked about the last, right? There's also beta random variables. There's also gamma random variables. And so, there's lots of different random variables that are used. And the difference between them is the type of density function that they have. Okay, good. All right, so then how do we find a density function? Right? So how do we actually obtain this? Turns out the probability density function and the distribution function are very closely related to each other. Right? And they're actually related through a simple derivative operation. So the probability density function. So usually for the probability density, we often denote that with a lowercase function f here. Okay. Right? Right. So this lowercase f is the PDF. Right? This is equal to the derivative of our CDF with respect to the thresholding parameter x. So remember this big F here, this is our CDF. Okay. So the PDF is equal to the derivative of the CDF. And then by that same token, you can also go in the reverse direction as well. So the CDF of the function is equal to the integral from minus infinity to infinity of the PDF. right? So they're very closely related. So if you have one, you can get the other one very, very easily. Just take a derivative or okay. Okay, good. Any questions on probability density functions so far? Okay. All right, so let's talk properties. Okay, so just like the CDF, the PDF also has its own properties. So first property, so probability density functions will never be negative. Okay. Okay. That doesn't make sense because we're still dealing with probabilities, and so there's no such thing as a negative probability. Okay. Right? Unless you're the Los Angeles Angels of Anaheim, the probability of them winning a World Series is negative 1,000. Right? Probability density functions are always continuous. Okay. So there's no discontinuities in a probability density function. It's always going to be one smooth curve. Okay. The third property here is that it integrates to one, right? And so this is related to our CDF, right? So remember, our CDF takes a maximum value of one because that's just the maximum probability. And so because the PDF is just the derivative of CDF, that means when you integrate it, it should go to one. Okay. Okay, so when you take the integral from minus infinity to infinity of the PDF with respect to x, this should give you 1. And I realize here that I did make a typo up here. I apologize. And so when you're computing the CDF from the PDF, the upper bound of the integral should not be infinity. It should actually be x here. Okay? So I apologize for that. So small correction on the equation that I wrote above. Because it wouldn't make sense otherwise. Otherwise, you'd integrate out to x. So for the third property, this when you take the integral from minus infinity to infinity, that always gives you 1. So this integral is correct. The integral at the bottom of the page is correct, but the integral from the definition or the relationship between the PDF and the CDF, that was I had a small typo there. So yeah, this upper bound of the integral here should be x, not infinity. Okay, and then the last property here, which again relates to the properties of the CDF, is that if we want to compute interval probability, okay. So in other words, the probability that our random variable falls between two bounds, right? So the probability that t is going to be, maybe greater than some threshold A or less than some threshold B, right? We know how to compute this based on the CDFs. And so for the CDFs, you just take the difference of the two values of the CDF. So the CDF evaluated at B minus the CDF evaluated at A. Okay. But then we can also compute this from the PDF as well, right? So we basically take the integral from the lower bound to the upper bound. Okay. So we take the integral from A to B of the PDF with respect to x. Okay. What's the question? All right, so those are the important properties for the PDF. Okay, so I know today's just a lot of math, a lot of just definitions, but all this kind of has a purpose. Because like I mentioned earlier before, right? When you're talking about uncertainty, when you talk about kind of randomness that can affect results, right? If you do experiments of any kind, it's something you're always familiar with. You run the exact same test twice. You're going to get different. You probably get different results just because of the uncertainty in the measurements. But usually, when that happens, you just say, I don't know, man. Uncertainty happens. Random stuff happens. But for the first time, we're kind of developing theory here. We're developing concepts for us to actually kind of grapple with that, to kind of actually deal with that in a more systematic kind of mathematical way. Right. So randomness does affect things, but that doesn't mean that we can't handle it. It doesn't mean that we can't actually work with it. Okay. So these are kind of the first steps that we need to take. All right. Any questions on these properties here? Okay. All right. So let's jump right into it then. So now that we have these mathematical expressions for the distribution function, for the density function, we can actually use these to compute things like the expected value, or in other words, what the mean is, the averages. We can also compute the variance. So we can compute mean and variance of a random variable. Okay. So we reviewed the concept of the mean and variance last time, right? But the equations that we went over last time required, lots and lots of different measurements in order to compute their values. Okay? So I would say the typical way to compute mean and variance requires actual multiple measurements to do that. So let me write out their equations here just to kind of refresh your memory. Okay. So the mean T bar, remember, is 1 divided by n multiplied by a summation. I is equal to 1 up to n of xi, right? So we basically just sum up all the different entries or all the different measurements or observations, and we divide by the number of observations that we have, right? That's pretty straightforward. And then the variance, so we can say the variance of t, so that sigma squared t is equal to 1 divided by n minus 1 summation. I is equal to 1 up to n of ti minus t bar quantity squared. Okay. So both of these equations, both of these definitions require a set amount of measurements, right? For the mean, technically you only need one measurement to compute the mean, but oftentimes you want more, right? So oftentimes for the mean, I would say you need, depends on the phenomenon, but the more measurements you take, the more accurate it's going to be. Okay. Okay. That's generally how we kind of understand these concepts here, right? So these ways to compute, or using these formulas to compute mean and variance, we often call these the sample mean and the sample variance. The reason for that is that you need samples, you need measurements, you need observation in order to compute this, okay? But when you're dealing with random variables, right, oftentimes you don't have measurements, you don't have observations for them. You know that if you take measurements, the value will change, but you don't necessarily know beforehand, what those measurements are going to be, or maybe it's just not feasible to collect a lot of measurements, right? So just to give you an example, right? In a lot of times when you're working in engineering testing, right? So let's say that you're testing a new design, you can't exactly afford to get a lot of data because maybe, let's say that you're doing destructive testing of some kind. So let's say you work for, I don't know, Toyota or something, and you're in order to test maybe like the vehicle crash system or the airbag deployment system, you need to crash a car to do that. You can't exactly build a ton of cars to do your testing because it's expensive to build a car, right? And so on the one hand, if you want to compute these variables, you have to compute 100 samples. Toyota's not going to make 100 Camrys for you to just ram into a wall to get your samples. So we need another way, right? We need another way to compute mean and variance that don't require a ton of samples to do. Okay. And so if we have a random variable and if we know its probability density function, there are mathematical expressions that we can use to compute the mean and variance. Okay. So there's actually formulas or there's actually equations that we can use to compute mean and variance and by extension standard deviation of a random variable if we know its probability density function. Okay. Okay. All right. So let's write out the expressions for this. And so let's do the mean formula first. Okay. Okay. So to kind of denote or to kind of specify that we're computing mean from a density function, we give it a different sample. We give it a different symbol. Okay. And so this right here is the mean of random variable t using its PDF. Okay, so we give it the symbol mu, right? So this is equal to integral from minus infinity to infinity of x ft of x dx. Okay. So you basically take the PDF, you multiply it by the threshold parameter x, and you take its integral from minus infinity to infinity. Okay. And then we can do the same thing. Oops, sorry. I always do that. We can do the same thing for the variance. So this is the variance of t using the PDF. All right, so this is integral minus infinity to infinity of x minus the mean. Okay, so in order to compute the variance, you do need the mean, and that's no different from the sample variance as well. Quantity squared ft of x dx. All right, so this is nice, right? And so this gives us a way, and oftentimes, even if you have a random event, right? Oftentimes you can make a fairly strong assumption in terms of what the randomness of that event is going to be. And so a lot of times, we can kind of pre-assign, we can kind of already define what what the probability density function would be for that random variable. And so based on that probability density function, we can compute its mean and variance without having to take any samples at all using these functions here. Okay. Okay. So a little bit more trivia, just because probability and stats, they just have a ton of terms, a lot of terminology. Sometimes the mean, right? Sometimes the mean goes by another name. Okay. And so because a random variable is one that oftentimes we don't want to sample, or we're kind of discouraged from sampling it too often. You know, technically the mean is not maybe the most accurate term. And so sometimes the mean is given the term called the expected value. Okay. And so that's the value of that's the value that we expect the random variable to take if we were to take a sample, if we were to take an observation or measure. Okay. But the whole point of using random variables is that we're not taking a lot of samples. We're not doing a bunch of tests, right? We use the random variable to account for its randomness, its uncertainty, and so so we give it the term expected value instead. Okay. All right. So let's put this in action. So let's see how we can actually use this with a very common distribution, our random variable. Okay, so like I mentioned before, there's lots of different types of random variables out there, and they're all characterized differently by different shapes of the probability density function. Okay, one of the most simple ones that you can do is called the uniform distribution. So the uniform distribution represents a random variable or a random event that can take any values between an upper bound and a lower bound. Right? Right? But the probability that it takes any value between those upper and lower bounds is flat, or it's even. Okay, so it can take any value between the upper and lower bounds, but it does not prefer any particular value between those bounds. Okay. Okay. So for a uniform distribution, a uniformly distributed random variable, the PDF looks like this. Right? So a uniform distribution, a uniformly distributed random variable has a flat PDF, and so it has a constant value. So it's 1 divided by b minus a when a is less than or equal to x is less than or equal to b and has a value of 0 everywhere else. All right, so graphically it looks like the following. So you have the lower bound a, the upper bound b. Yeah, so it kind of just looks like a square pulse, just like that. All right, so what the uniform random variable says that we can take any value between a and b, but which value that we choose is completely random because it's it's all the probabilities are flat in that region. Okay. Okay. So for a uniformly distributed random variable, what we want to do is we want to compute. We're going to compute the mean and the variance. Okay. So all we're going to do is we're going to basically take this formula for the PDF, plug it into these formulas here for the mean and variance, and then use that to compute their values. Okay. Okay. Any questions on just the setup for this example here? Okay. All right, good. Okay, so let's start with the mean or the expected value. So the mean of t, the function, well, it's just the mean of t, okay, is equal to integral from minus infinity to infinity of x, ft of x, dx, okay? Okay, so let's go ahead and plug in our function here, and note that our function is only defined between a and b, okay? It's 0 everywhere else. And so that's going to define the bounds of our integration. So instead of integrating from negative infinity to infinity, we're only integrating from a to b. All right, so we have integral from a to b of x. And then we're going to multiply by the PDF in that range, which is just 1 over b minus a dx. All right, so we have a pretty straightforward integral here because our uniform distribution is constant within that range. And so we can take the 1 over b minus a and just factor it out because it's just a constant, right? So this is 1 over b minus a integral from a to b of x dx. Okay. Okay. So we integrate x, we just end up with x squared over 2, evaluated from a to b. Okay. We go ahead and evaluate that. We have 1 over b minus a multiplied by b squared over 2 minus a squared over 2. Right. I'm going to factor out the 1/2, and then we have a b squared minus a squared up top. Okay. B squared minus a squared, we're going to use kind of the simple arithmetic kind of expression here. So b squared minus a squared is equal to b plus a multiplied by b minus a, right? So that's kind of a simple FOIL trick that we can apply. Okay. And so we apply that, we get 1/2 multiplied by 1 over b minus a multiplied by b plus a, b minus a. Okay. Right. We have a b minus a in the numerator, a b minus a in the denominator, so those are going to cancel out. So that cancels out with that. This is equal to b plus a divided by 2. Okay. So the mean value or the expected value of our random variable t is just the average between the upper and lower bounds. Okay. And that makes sense, right? So we know that for a uniform random variable, our variable can take any value between a and b, but the distribution is flat, right? And so if we take, let's say, 100 samples of this random variable, we're just going to land in random spots in between a and b. And so the average between all of those should be right in the middle, right? So that's b plus a divided by 2. All right, any questions on the mean for this random variable? Okay, All right, so let's compute the variance, right? This one's a little bit more cumbersome just because of the square, but we can go ahead and do it. Okay, so the variance of t in this case is integral from minus infinity to infinity. We have x minus the mean value, quantity squared, multiplied by our PDF. Okay. Okay. So let's go ahead and plug in for everything. So we'll plug in for the mean. We just found that. And then we'll plug in for the PDF as well. Same thing that we're going to do, same thing that we did for the mean value. Since the PDF is only defined between A and B, that's going to change our integration bounds. So we're going to have integral from A to B of x minus b plus a divided by 2, quantity squared, times 1 over b minus a dx. Okay, so 1 over b minus a, just like before, is a constant, so I'm just going to pull that out. Just to make the integral a little bit easier, I am going to FOIL out the square term there. But of course, you can integrate this with u substitution as well. That should also work just fine. Okay. And so we have equal to 1 over b minus a, integral from a to b. If we FOIL this out, we get x squared minus b plus a times x. Okay. So it's 2 times x times b plus a divided by 2. So the 2's cancel out. We just get that. Okay. And then plus b plus a quantity squared divided by 4 dx. All right, so let's go ahead and perform the integration with respect to x, right? And so the b and a are constants, so we're going to leave those alone, right? And so we have 1 divided by b minus a multiplied by x cubed divided by 3 minus b plus a divided by 2 x squared plus b plus a quantity squared divided by 4 times x. Okay, evaluated between x is equal to a and x is equal to b. All right, so we have a little bit of a mess on our hands. So, not too difficult of an integral to evaluate, just the algebra just is going to get a little bit messy. Okay, so let's go ahead and begin. Okay, so I'm going to evaluate everything there at x is equal to b. So we have b cubed divided by 3 minus b plus a multiplied by b squared divided by 2 plus b plus a quantity squared divided by 4 multiplied by b. Okay. And then we're going to subtract the entire thing, evaluate it at x is equal to a. So we have minus a cubed divided by 3 plus b plus a times a squared divided by 2 minus b plus a quantity squared divided by 4 times a. All right. So I think we'll just kind of do this we'll kind of finish this up for the rest of the class today, and then we'll call it for today. There is a bit more to these lecture notes, but we'll continue that after the midterm. Okay. Okay. All right. So let's go ahead and distribute a lot of this stuff. And so basically any term here, or the strategy that I'm going to use, is that any term here that is not fully distributed, so something like that, something like that, something like that, something like that, right? I'm going to go ahead and FOIL all those out and distribute it so that we have just a clean amount of terms that we can just compare, okay? All right, so we have 1 over b minus a multiplied by, I'm going to go ahead and group some terms together as well, just to kind of make things a bit simpler. So both the b cubed over 3 and the a cubed over 3, I'm going to group those together, okay? So we have b cubed minus a cubed divided by 3, okay? And just so that I'm staying organized, since I've already brought those terms down, I'm going to go ahead and cross them out in the term above, okay? Minus, let's see, b cubed divided by 2 minus ab squared divided by 2 plus, okay, we got to FOIL this guy out and then multiply by b. And so this is b squared plus 2ab plus a squared multiplied by b divided by 4. Okay. Plus a squared b divided by 2 plus a cubed divided by 2. Okay. Minus, same thing here. So b squared plus 2ab plus b squared, or plus a squared multiplied by a, all divided by 4. Okay. Okay. You can already see that we have some common terms here that we can combine together. So the b cubed, a cubed terms, those can be combined, right? But we still have some b cubed and a cubed terms that are coming from the other terms. So let's combine them first, and then we'll go from there. Okay. So let's combine the b cubed terms first. We have b cubed divided by 3 minus b cubed over 2. Okay. That's going to give us a minus b cubed divided by 6. Okay. Right, so we have equals 1 divided by b minus a multiplied by minus b cubed divided by 6. Okay, so that's 1/3 b cubed minus 1/2 b cubed. Okay. Okay. And then we have the a cubed terms. We have a minus a cubed divided by 3 plus a cubed divided by 2. Okay, so that's this term. Use a different color. That's this term and this term here. Okay. So those two are going to combine together to be a positive a cubed divided by 6. Okay. Okay. I'm going to bring down the ab squared term and the a squared b term because those ones we can't do anything with them now. So minus ab squared divided by 2 plus a squared b divided by 2. Okay. Plus, now we're going to distribute this. And so we have b cubed over 4 plus 2ab squared divided by 4 plus a squared b divided by 4. Okay, so that's this entire term right here. Minus ab squared divided by 4 minus 2a squared b divided by 4 minus a cubed divided by 4. Okay. All right, almost there. We just got to simplify just a little bit more. Okay. All right, and so last simplification here. So let's combine the b cubed terms once again. So we have b cubed minus b cubed over 6. We have a plus b cubed over 4. I believe those are the only ones. And so we have 1 over b minus a So b cubed over 4 minus b cubed over 6, that is a positive b cubed over 12. Right? Because b cubed over 4 is 3 over 12, minus b cubed over 6 is minus 2 over 12, right? So that combines for that. And then we're going to have the same thing for the a cubed terms. Okay. So that's going to be a minus a cubed divided by 12. Okay. Good job for all those. Okay. Okay, now let's look at the AB squared terms. And so we have a positive or negative AB squared over 2. We have positive AB squared over 2, so those two terms are going to cancel out. Okay. Next, we have the A squared B terms. So we have a positive A squared B here, negative A squared B here, so that's going to cancel out there. Okay. And then all we're left with is a positive A squared B divided by 4 minus AB squared divided by 4. Ran out of time. I apologize. I thought I could finish 4 before we finished up. Okay. But we're just about there, right? And so we just have to do a little more simplifying here. Okay. So the last couple of steps of the simplifying is that eventually you're going to get the inside of this term here, okay, to essentially become b minus a quantity cubed. Okay. Divided by 12, actually. Okay. All right, so that's kind of the last step of the simplification. And then this cubed here, of course, is going to cancel out with the b minus a on front, right? And so what you get from this is that the variance is equal to 1 over 12 b minus a quantity squared. All right. I'm sorry. I thought I could finish up, but the algebra always kind of tricks. It always takes longer than. But the full details of that are in the lecture notes, so you can definitely check it out. So when we come back on Tuesday, obviously we're taking the exam, and then when we come back next Thursday, we'll finish up just the last 2 pages of these lecture notes. Okay. So thank you guys for coming today. I apologize for going over a little bit. I wish I could finish that up. Hope you guys have a good weekend. If you have questions leading up to the exam, don't be afraid to send me an email. So I will be available for email tomorrow and on Monday. And I remember I have office hours on Monday and Tuesday as well before the. Okay. So thank you guys for coming. I hope you guys have a good weekend, and I will see you guys next week. You too, Anthony. Thanks, guys. You too.